So this question asks for the expression for the electric potential inside a capacitor. So to begin, we'll use our relationship between change in electric potential and electric field. So delta V is equal to minus the integral of E dot ds over some path S. So let's think about this E dot ds. We know that E dot ds is the scalar product between E and ds. So it would be the x component of electric field dx plus the y component of electric field dy plus the z component of electric field dz, and do the integral of those guys. Let's think about the different directions. What do we mean by the components? Where's our coordinate system? So let's take x, y, and z the usual way. So in our capacitor, we have our positive plate here, negative plate here, so the electric field points towards the left, tells us that the x component is negative. So the x component of electric field is negative the magnitude. The y component is 0, and the z component is 0, because the electric field only points towards the left. If we wanted to put in a value for the electric field, we know that the magnitude of an electric field between the plates is given by the charge density divided by epsilon naught. So we could put that in if we wanted to. We also remember that charge density is charge over area. So there's the details of our electric field. For our path S, let's go from some initial point to some final point. Doesn't really matter where. Let's go from here to here. So there's our path S. So our path S has an x component that comes here and a y component that comes here. So we see the x and y parts. So let's think about this in terms of our integral over here. The y component of electric field is 0, so this part is 0. The z component is 0, so this part is 0. We're left with minus the integral of ex times dx. Let's put in what our electric field is, minus E times dx. E is a constant. We know it's constant between the plates of a capacitor, so minus times minus gives us a plus. Then our electric field comes outside, and we've got the integral of dx. The limits of our integral will be from an initial point to a final point. If we're talking about the change in potential between the plates of the capacitor, it makes sense to take our initial point here and our final point here. Let's go from one plate to the other. So for our initial point, this distance is x equals 0, and for our final point, x equals s, because we call the distance from the negative plate s. So there are our limits. So the integral of dx is just x. It's going to be evaluated at s and 0. So we get e times s minus 0 to get plus e times s, the potential difference between the plates of the capacitor. And that's the result that we were expecting.